Some problems just seem, well, impossible. And in the energy industry, one of the biggest challenges has always been trying to measure this chaotic, high-pressure mix of oil, gas, and water as it literally blasts out of the ground. So let's dive into the story of a device that actually does the impossible. Just try to picture this for a second. Deep underground, you've got this violent cocktail of stuff rocketing through a pipe. It's not some smooth, predictable stream. No, it's a turbulent, churned-up mess, which makes figuring out exactly how much oil, gas, and water is in there incredibly difficult.
And that's really the big question, isn't it? How do you get precise, real-time data from something so chaotic? For years, this has been a massive headache for the industry. But to really appreciate the solution, first, we gotta understand the problem itself.
All right, so what are we really up against here? Because this isn't just about measurement. It's a fundamental challenge in physics and engineering. The technical term for this hurricane in a pipe is multiphase flow. It's basically any flow that has more than one state of matter all mixed together. So in our case, we've got liquid oil, liquid water, and gas all jumbled up. And this stuff can be anything from a thick, heavy sludge to a wet gas that's full of liquid droplets. So how did they used to handle this? Honestly, brute force. They would literally divert the entire flow into these massive separator tanks and then just wait. They'd wait for gravity to slowly separate everything out so they could measure each part individually. It was slow, it took up a ton of space, and the numbers you got were basically just a good guess.
But what if you didn't have to separate them at all? What if you could measure everything instantly, right there inside the pipe? Well, that's where the revolution begins.
And here it is. This is the Vx Spectra flow cytometer. It's this compact, super robust piece of tech that's designed to do everything those giant tanks did, but it does it in a fraction of the space and in real time. It's a complete game changer. And this really puts it in perspective. You're going from something that's huge, slow, and based on approximation, to a compact device that gives you precise, continuous data. This isn't just a small improvement, It's a totally new capability for the people running these operations.
So the big question is, how does it actually work? How does this little device see inside that chaotic mess and tell you exactly what's what? All right, let's pop the hood.
The whole process is this elegant three-part system. First, you've got a classic physics, a Venturi tube, that measures the total speed and volume of the entire mix. Second, a very sophisticated nuclear system scans the flow to figure out the exact percentage of oil, gas, and water. And third, a powerful computer right on board crunches all that data instantly. And what's so slick is how seamlessly these three parts are integrated into one unit. The flow zips through the Venturi, it gets scanned by the nuclear detector at the exact same time, and boom, the computer gives you an instant readout. It's like a perfect symphony of physics, nuclear science, and computing. But the true innovation, the real secret sauce, is in that nuclear system. It uses a technology called full gamma spectroscopy, and this is what sets it apart from everything that came before it. Think about it like this. An older meter is like standing in a concert hall and just knowing that the orchestra is loud. But full gamma spectroscopy, that's like having a master sound engineer who can listen to that same orchestra and tell you the precise volume of the violins, the cellos, and the trumpets, all individually, all at the same time. Let's actually see what that looks like. This graph? This is what an older conventional meter sees. It's only catching a few little data points from the energy spectrum. It's like trying to watch a movie through a keyhole. You get bits and pieces, but you're missing the whole story. And now, look at this. This is the VMX Spectra's view. It's not a keyhole, it's the full-on, high-definition IMAX screen. It sees a complete, continuous picture across the entire spectrum. No more guessing, no more approximating. It is capturing a dataset so rich and detailed that the measurements are incredibly accurate. Okay, so we have this amazing high-definition data. But what can you actually do with it? Let's talk about why this actually matters in the real world. Well, the benefits are just enormous. You get accurate data no matter how wild the flow gets. You save a ton of space and money by getting rid of those huge separator tanks. You get real-time info to manage the whole operation better. You can even run these things remotely, and they work with pretty much any kind of oil or gas. And that raw data doesn't just get dumped in a spreadsheet somewhere. Nope. It's fed into software that turns all those numbers into clear, useful information. Operators can look at a single screen and see the health of every well, track trends, and spot problems before they get serious.
Ultimately, this is what it's all about: empowering people. Better data leads to smarter decisions. It allows engineers to optimize production, manage resources way more efficiently, and get the absolute most out of every single well, all because they can finally see what's actually happening inside that pipe.
So this technology doesn't just solve an old problem, it really points the way toward a brand new future for how we manage energy.
And this wasn't an overnight success. The journey started way back in 2000, when the first Vx technology set a new standard. Today, the Vx Spectra is at the absolute cutting edge, and the future it's creating is one driven not by estimates, but by precise, real-time understanding.
When you strip everything else away, that's the real story here. It's about a fundamental shift. We're moving away from an era of just approximating and making educated guesses and into an era of precision, clarity, and true understanding.
It really leaves you with a fascinating thought, doesn't it? This was once considered a nearly impossible measurement, and now it's done routinely. So it makes you wonder, if we can solve this, what other seemingly unmeasurable problems are we going to tackle next?